A silicon chip measuring 5 mm on a side and 1 mm in thickness is embedded in a ceramic substrate. At steady state, the chip has an electrical power input of 0.225 watts. So essentially, just a very small amount of power is entering through the chip. The top surface of the chip is exposed to a coolant whose temperature is 20. The heat transfer coefficient for convection between the chip and the coolant is 150, and if heat transfer by conduction between the chip and the substrate is negligible, determine the surface temperature of the chip in degrees Celsius. So essentially, what we have here is a problem in semiconductors, right? How do you cool a chip? Now, let me show a sketch of the problem so that we could, analyze this properly. Okay, so we have here that thing, the coolant, you know, um, being cooling this chip. So we have this chip, this green one, 5 mm by 5 mm. So it's a square chip, but the thickness is 1 mm. But the area exposed to the coolant is just this outer, the top surface, right? So the area really in this case will just be equal to 5 mm by 5 mm, right? This area only, okay? So that's 5 mm by 5 mm. So in terms of area, that will be, so the area exposed to the coolant will be 2.5 times 10 to the negative 5 m squared. Quite a small area. Anyway, the chip is also small. Then, so that's the idea. So here our system will be the chip, and essentially we can just do the analysis also like the first law of thermodynamics. Delta U is equal to Q plus W. Okay, and since this will be what there's no mass entering and leaving your chip essentially is a closed system. Okay, so this equation when written on a differential form will become really like du dt, like change of that with respect to time, dq dt and dw dt. Well, in this case, um this since we know that this is in steady state and use internal energy will no longer be changing, right? Because things are going steady. Since the chip will be subjected or will now have a steady state condition, temperature will no longer be changing. It will be maintained somehow. We don't know yet as of the moment. We're looking for that, and it will not be changing. Therefore, this will be just be zero. Okay, it will be zero, and this dq dt will just essentially be the q dot, the rate of heat transfer, and dw dt will just be w dot, rate of work done or being done to your system. So in this case, we're looking for the temperature. So we're looking here for a temperature of the chip, which is related to a Q because we are given the um, the heat transfer, right? We are given heat transfer the coefficient. In this case, 150. Okay, let me work with that first. I think it's not that clear as of the moment. So since the chip is hot, it will be a temperature. Let the temperature of the chip be TB. It's quite hot. The chip will be releasing heat to the surrounding in this form. Q dot equal to negative. Negative stands for heat being released to the surrounding. Uh, the equation here will be H A delta T, in this case TB minus TF. This is really convective heat transfer. H in this case will be given by, H in this case is given by 150, so negative 150. And the area in this case is this, area exposed to the coolant. It's 2.5 times 10 to the negative 5. Okay. And TB is we don't know yet as of the moment, and TF is known. The TF, the temperature of the coolant is 20. Okay, so therefore we'll be able to get that as long as we be able to solve for our q dot. We don't know q dot first as of the moment, so let's try to solve for q dot from here. Now, what is w dot? In this case, there's only two forms of energy transfer. One is being heat being released, and the other one energy being added through an electrical power input, meaning this system is being charged or current perhaps is flowing. That's why it's being added with that energy point or power 0.225 watts. What do you mean by that? 0.225 watts. We could think of that as electrical work, because work actually here could mean that W there could mean boundary work, meaning the system could expand or contract. In this case, it's not. It could mean shaft work, like there's a rotating shaft that do work to your system. In this case, there's none. Or it could be electrical work. Okay, meaning energy is added through an electrical form. So in this case, we think of that as energy or work being done to your systems. In this case, we'll have Q dot plus, since work is being done or energy is being added, so it's a plus, meaning, okay, the system gains energy for that. So we'll have here 0.225 watts. Okay, W is watts. So therefore, that's equal to Q. Okay, Q dot, so 0.225 watts. And actually, if you can look at the units here, the unit will also be in terms of watts. So therefore, if you put the from here, it's clear that Q will be equal to negative 0.225, right? So if we put that negative 0.225 in here, we'll then be able to compute for TB. Okay, so meaning the heat at the temperature um, of your the surface of your chip will be equal to TB. So TB therefore, based on that, is equal to 80. No, there's no negative. It's equal to 80 degrees Celsius. So it's quite a hot surface. So your chip really is hot. That's why more or less most of your devices, like laptops perhaps, will really have a cooling fan that's supposed to be working so that the chip will not be fried, because the temperature will really increase due to the power consumption of the chip, like the operation that it processes per unit time. So in this case, 80 more or less is a good operating temperature, meaning the chip could still work properly at that time. Perhaps beyond 100 or beyond 120, the chip could be destroyed out of the process. So cooling fans, or in this case a coolant, maybe more or less this is a fan based, like air is being used to cool this chip. I hope so. So I think that's it. So that's how we compute the steady state temperature of the chip using just the very simple first law equation of thermodynamics, delta U, change in internal energy is equal to Q plus W. Thank you.